Hello all to this webinar in our Smart Engineers YouTube channel. I want to welcome you, everyone. Hello all to this webinar in our Smart Engineers YouTube channel. I want to welcome you, everyone. Thank you to attend this webinar. This webinar is sponsored by IEEE City University Student Branch. Really, today we will join us, as we mentioned before, with this webinar, and we will create more than this webinar, webinars related to electromagnetic, antenna, or any field will help our committee. So today we have with us Dr. Solomon Mingle from University of Birmingham. Today he will talk with a special or fantastic topic related to leaky wave antenna, which is titled here, Analysis and Design of a Compact Leaky-Wave Antenna for Wideband Broadband Radiation Application. So today, Dr. Solomon will guiding us.
Its region, and so it's an opportunity to learn much about this. So before I start, I'll quickly talk about these three areas. When I talk about without stop-band application, it means one can take this idea that we're sharing with this community, and out of that, you can be able to design your own antenna and use it at any frequency you prefer. But before you can do that, you need to have certain parameters, which we'll be talking about very soon. So to start with, let's look at the itinerary or the outline for our webinar for today. So first, we'll be looking at the introduction of our design and its parameters. Secondly, we'll be looking at the advantages and applications. Thirdly, we'll be looking at the basic principles and its operations. Fourthly, we'll be looking at the antenna design and the parameters, and the antenna design procedures, feeding port design, which is very important. Then we'll look at the unit cell analysis, and we'll be looking again at the beam scanning leaky wave antenna. This is the area which will benefit most of the engineers who wants to take this particular project on board. And I think finally, we'll be looking at a video demonstration how this antenna was designed. So we have a great opportunity ahead of us. As you can see with this outline, we will benefit a lot from this particular webinar. So if you have a pen and paper, you can take up notes and you can put your questions underneath once we finish. So let's start with the introduction. So with the introduction, we're talking about leaky wave antenna. And this type of leaky wave antenna we're talking about is very simple to fabricate. Therefore, it offers a broadband radiation properties. And that design is basically going to be based on a V-band for today. That is our aim for the design. Like I said, this antenna has a very wide range of beam scanning. And as you can see, it can scan from minus 65 degrees to 25 degrees. And gives us a very huge, wide range of scanning of about 90 degrees. And this sort of antenna has not got any property of electronic gadgets on them. It's very simple, unlike other antennas whereby they use electronic components or active components to be able to scan the beam. This antenna does not use any of those components. It's just a simple antenna that will give you a very wide beam scanning. And as you can see, we have again for this particular V band at 16 dB. And we'll be looking at the design very soon. Now let's look at the advantages. As you can see, an antenna that we are discussing today has got so many advantages, antennas which are there on the market. One, fulfill the demand of modern high rate and speed communication. Two, this antenna can be applied for remote monitoring for vital signs. Secondly, we can also use it for imaging and radar systems. Some of the areas that we can look at using this application are in the hospitals, immigration, fire service, and so forth and so on. And thirdly, one big advantage is the beam scanning capabilities. As I rightly said in my previous slide, the antenna has got a very good beam scanning properties, and we'll be looking at it in details. Furthermore, this antenna is a low profile. It is lightweight and is easy to integratable, and it is easy to fabricate as well. And so you can see clearly that what we are discussing today, we're going to have a very good benefit of it. And finally, this provides an impedance bandwidth along with high gain. That means we can have a very narrow beam. And how to get a narrow beam, we'll demonstrate this at the end of the application. So let's look at this next itinerary. So this is the antenna we'll be talking about today. On your screen, as you can see, we have the antenna design parameters. Now, the area we'll be concentrating on involves one, the feeding part, the unit cell, and the full structure. When I'm talking about the full structure, as you can see, the antenna has got a ground which we've labeled with some parameters. And those parameters are very important to be able to achieve the desired scanning capabilities we've discussed earlier on. But before you can design this, you need to know a few areas concerning this antenna. One is the unit cell area. And this unit cell area has got a particular parameters which we'll be looking into that, how this antenna was constructed. Another area we'll be looking at is the feeding part or the feeding network, and what constitutes that feeding network to make this great antenna very scannable. As you can see, this antenna has not got any electronic components. It's only made of dielectric and copper materials and feeding port. How this magic operates, we'll be looking at it in a few minutes. So we're going to move on how this is designed. So we'll first look at the parameters which I just talked about. Now, the basic structure of the proposed antenna with the feeding network is used in a simulation. It is shown in Fig 1, which I just showed you. Now, the area that I want you to pay attention are the parameters which I talked about. Now, the 2A will represent our width, the B will represent our thickness of the dielectric, the B is the period of the perturbation, means the hole that is created in the antenna, and the D is the diameter is involved in the hole. And other parameters involved are the W and then the TY, which are the width and then the tapered length of the substrate. So going back to the slide, if I should go back, you can see that all these parameters has been put on your screen. We have the WG, which is the width of the copper plate, the length of the copper plate, or the ground plate is the LG, and you can see the TY and then the W are the feed netting capacity, which is illustrated on your screen. And then we have the unit cell, which has got the length and breadth and the height of the substrate. So going back to where I was before, these parameters are the areas that are very, very important for our design. For anyone who is interested in this particular antenna, you need to contact us and I will give you those parameters for your design. Furthermore, we move on to the next stage. There are three important parameters which I want you to take note if you want to get involved into this design. And they are, one, the substrate thickness. Now, the substrate thickness performs the magic for this antenna. And so we'll realize that this antenna has not got any electrical properties, electronic properties on them. It's only substrate with some holes in them. And this holes has got a width of it. And this holes as well has got a length. And we represent those substrate with B and 2A. How this came about, I will explain in the next chapter. Now, the reason why we're using this substrate is because the substrate will keep the radiation loss to minimum. And so we will need a particular substrate which has got a very high dielectric density. And the substrate that we chose has dielectric of 10.2 with a tangent of 0.023. And this was used in our design. And so to achieve a beam scanning, you will need this particular substrate from Roger 6010LM. And this particular substrate has got that property that will perform the magic for your beam scanning. So please take note, this particular substrate is the main component that performs the magic for our design. Bear in mind, you need all those parameters which I've just talked earlier on. Now, let's move on to the antenna design procedure. Now, as said earlier on, those parameters which I've just said have been used in the design. And after selecting our substrate, we are now left to select the thickness, the width of the dielectric. And so to have the confinement of this radiation within without causing it to despair, we need to apply certain formulas which have a single mode operation and which can confine the radiation within. And this can be referenced in the subsequent chapter, which I'm going to demonstrate very soon. On your screen here is the parameter B, which is equivalent to the parameter A. Bear in mind that parameter A is the width of the unit cell, which I demonstrated to you earlier on. And so if A is equal to B, we can therefore use this particular formula to calculate the B, which is the height of the substrate. This will give us an idea how we will be able to construct our unit cell, and therefore we will be able to take the reflection coefficient to proceed to the next stage of our design. At the same time, if you look at this equation, if we are operating at a particular wavelength of 59 gigahertz, we will achieve the B value to be 0.635 millimeter, which is the lambda for that particular B band at that resonant frequency. Therefore, by applying the formula, you can say that the width of that unit cell will be equivalent to 1.562, which is taken accordingly from optimization if needed. Next, we'll look at the generation of the leaky-wave antenna. And this particular generation of the leaky-wave antenna is taken from a reference book, which I have referenced at the bottom. And this reference book is I've made use of this particular line in a different way, but the concept is different in our design. Our design has more beam scanning as compared to the reference which is made in 15, which I will demonstrate to you in a few minutes. In demonstrated here on your screen, where BN and BO are the N and the N are the fundamental space harmonic respectively. And like I said, P is the period and N is an integer. Therefore, by so doing, if we know the value for N and P, we'll be able to know the angle at which we want to operate. And this can lead to another area where we can find the design of the scanning of the angle where the beam is going to scan. Hence, lead us to the third equation where we have theta equals sine inverse of DO over KO. You know, KO on your screen, as you all know, is the free space wave number at the frequency of our interest. And in this webinar, because we are designing it at V band, we are interested at a particular frequency of 59 gigahertz, and that's our center frequency. So using that particular period, which we know, and wave number, we'll be able to know at each frequency the angle at which the beam is going to scan. And that is the equation number 3 on your screen. For example, if I know the wave number and I know the number of holes, which is the P, and I know the BO, which is the fundamental space harmonic, and I take the inverse at, let's say, 50 gigahertz, I'll get a specific angle where the beam is going to go. If I take 51 gigahertz and I take its wave number and I put it into the equation and I scan the beam, I will know the angle at which this particular frequency will be, and so forth and so on. So if I take 50, 51, 52, 53, and so forth to 66. So now that we've been able to discuss the unit cell, now we've put everything together to have a full wave simulation of the whole antenna. Now on your screen here is the result of the S11, and you all know that S11 represents how the power is reflected from the antenna, and hence it's known as the reflection coefficient. As you can see, this antenna S11 has got a very good reflection coefficient because it demonstrates that the S11 is below the minus 10 dB line. That means that we'll have 90% input power is delivered to the device, and its reflected power is less than 10 degrees, 10%, which is really good. As you can see on your screen, if you cut from the S11, you can see that the antenna has got a very good S11 from 50 gigahertz to almost 65.5 gigahertz. That's a very big wideband. That is why we are using this particular design. Moving forward to the other results, we are going to look at beam scanning capabilities. Now, because the antenna gave us a very good wideband, and as I explained in the theory earlier on, we can scan this beam from the back to the forward. So on your screen here, we chose some certain frequencies from 50 to 67 gigahertz. And as you can see, at 50 gigahertz, as we scan, we had beam scanning from 53.47, okay? And at 67 gigahertz, when we scanned the beam, we had 25.8 degrees. And so total of this particular antenna is almost 90 degrees, or more or less 90 degrees or 70 degrees, as you can see on your screen. This tells you that we can use this particular antenna in various applications, because you can have this antenna to behave as a bidirectional antenna, depending on whatever you are using it for, either for MIMO antenna, either for millimeter wave antenna, either for directional antenna. Any particular application you want to use this antenna, you can use this. And so for today, we're going to look at one specific area where we can apply this particular bidirectional antenna in front of us to be able to take up certain applications in terms of measuring vital signs of human beings. Before we do that, let's look at some of the old parameters which are there already. As you can see on your screen, monitoring vital signs.
And this webinar, as Dr. Solomon said, we have another webinar related to signal processing. As he mentioned, I don't mention anything till now, but he mentions that. So we have many webinars in our channel related to different topics in our society, related to electromagnetic antennas, signal processing, everything that will help us in our study. Thank you all to be here. Thank you, Dr. Solomon, to present for us. And thank you all. Hello all to this webinar in our
technique to achieve your desired goals. So over to you, Ihab.
Thank you. What I want to say for all attendees, thank you to be with us in this webinar. As Dr. Solomon said, we have another webinar related to signal processing. As he mentioned, I don't mention anything till now, but he mentions that. So we have many webinars in our channel related to different topics in our society related to electromagnetic